Radioactive decay rate. Radioactive decay of any one nucleus is a totally random event that is not affected by temperature, pressure, or being part of a compound. However, if we have a large number of nuclei, we can predict roughly how many will decay in a particular time. In a similar way, we cannot predict when we will get a 6 when throwing a die, a single dice. But if we threw 6,000 dice, we could be confident in getting very close to 1,000 sixes each time. The activity of a sample is the number of actual decays taking place per second, and is measured in becquerels, given the symbol uppercase B, lowercase q. 50 becquerels means there are 50 decays every second, for instance. The activity will depend on how likely a particular nuclide is to decay, and how many unstable nuclei are present in the sample. So we get the equation activity A is equal to lambda n, where A is the activity in becquerels. Lambda is what is called the decay constant. This depends on the particular nuclide and has units of seconds to the minus 1. And n is the number of unstable nuclei present. Note that the count rate is the actual number of decays detected, and this is measured in seconds to the minus 1. This will be lower than the activity, as not all the decays will be detected. Many will miss the detector or will be absorbed before reaching it. Often you'll be given the mass of a sample in grams. To find the number of nuclei present, we divide by the atomic mass to find the number of moles present, then multiply by the Avogadro number to find the number of nuclei. For example, a sample of 2 grams of carbon-14 contains 2 14ths, which is 0.143 moles. 14 grams would contain 1 mole. This then contains 0.143 moles times 6.02 times 10 to the 23, Avogadro's number, the number of nuclei in a mole. This gives 8.6 times 10 to the 22 nuclei. As a nucleus decays, it changes to a different nuclide and cannot undergo that decay again, though it may undergo one or more different decays as part of a chain. We can say that the activity is equal to the rate of change of unstable nuclei, which we can write like this. Activity A is equal to the rate of change of nuclei with respect to time. We can write that this is equal to minus the decay constant lambda times n, the number of particles. This is what we found previously. The minus sign shows us that the number of nuclei is reducing. This is decay. When the rate of change of something depends on the number present, we get what is called exponential change. The exponential decay relationship leads to this equation, which you don't need to be able to prove, just to be able to use. In this case, n is the number of nuclei remaining after time t. n0 is the number of nuclei at the start at t equals 0 seconds. E is the exponential function, which again you need to know little about, but you do need to know how to use in these particular cases. Lambda, as we met previously, is the decay constant. As the activity and the mass of the sample are both directly proportional to the number of nuclei, we can also say that activity A will be equal to the initial activity times e to the minus lambda t, and the mass will be equal to the initial mass times e to the minus lambda t. The count rate will also fall at the same rate, giving count rate C is equal to the initial count rate times e to the minus lambda t. Let's just run through an example. A radioactive sample has an initial count rate of 200 counts per second. If the decay constant is 2.0 times 10 to the minus 3 per second, what will the count rate be after 2 minutes? Well, for this, we can use the count rate is equal to the initial count rate times e to the minus lambda t. This comes out at 200 seconds to the minus 1 for the initial count rate, is equal to e to the minus lambda, which is 2 times 10 to the minus 3 per second, times the time in seconds, 2 minutes, is 120 seconds. This gives a count rate after 2 minutes of 157 counts per second. Next we're asked how long will it take the sample to decay to a count rate of 80 counts per second. Well, again we use this equation, but now if we take natural logs of both sides, we get the natural log of the count rate is equal to the natural log of the initial count rate. Here the factors are multiplied together and the logs then get added together, so we must add the natural log of e to the minus lambda t. But the natural log of e to a power is simply the power itself. So we can write ln c is equal to ln c naught minus lambda t. We need to find the time t, so if we rearrange with t as the subject, then putting in the numbers, the initial count rate was 200, the count rate at the time we're trying to find was 80, and the decay constant 2 times 10 to the minus 3. Putting in the figures for the natural logs gives us a time of 458 seconds. Exponential decay leads to a graph something like this, where on the y-axis I've got the number of nuclei as a percentage, and on the x-axis time, and I'll add some arbitrary units. What we find now is that if we look at the time to drop to half, here we have 100%, so if we go across at 50%, we see it takes 1 unit of time. If we look at the time to drop from 80% to 40%, that is this time, which again is 1 unit. Going from 60% to 30%, again takes 1 unit. So we find that, as with any exponential change, the time taken to change by a particular fraction is a constant. For radioactive decay, we consider the time taken for the sample to halve. We call this time the half-life of the sample. At the half-life, the number of nuclei remaining is equal to half the original number of nuclei. So we can write that n is equal to n naught over 2. Or rearranging, we get n over n naught is equal to a half. We know that n is equal to n naught e to the minus lambda t, and we can rearrange this to give n over n naught is equal to e to the minus lambda t. Substituting in now for a half here, we get that a half is equal to e to the minus lambda t. If we now invert both sides, the inversion of a half is just 2. Inverting this side, we lose the minus sign on the power, to give 2 is equal to e to the lambda t. Taking natural logs of both sides, we get the natural log of 2 is equal to lambda t. And so we can rearrange to get the half-life, t subscript half, is equal to the natural log of 2 over the decay constant lambda. So also we can find that the decay constant is equal to the natural log of 2 divided by the half-life. Make sure that you give the half-life in seconds. It will often be given in a question in minutes, hours, or even years. Going back to this equation, if we again take natural logs of both sides and rearrange, we now have a variable is equal to a constant times a variable plus a constant. So, if we plot a graph of the natural log of the number of nuclei against time, we should get a straight line with the y-intercept being the natural log of the initial number of nuclei, and the gradient will be equal to minus the decay constant. Of course, you could also plot a graph of the natural log of the activity against time, the natural log of the mass against time, or the natural log of the count rate against time.